All right. Well, hi, I'm Bill Magro, and I want to thank the organizers for the invitation to speak. Don't think I could have had a better introduction than the last session and the discussion that followed it. So my own background is very much as a user and applications person, a computational physicist who got interested in computers and came in from the outside in, played with MPI implementations very, very early, led the development of MPI software and Open Fabric software at Intel, always working from the top down. And I didn't know much about InfiniBand. I didn't know much about RDMA when I started. And the more I learned, the more we were able to do with it, but the more we learned about where it made our lives difficult, to the points that were being made just a moment ago. Maybe MPI developers haven't been well received in this forum. I'm here to represent the MPI developers. So let me charge forward. First thing I want to talk about is the fact that HPC, and this is an HPC-centric talk, but it's not an HPC-exclusive talk. Just a second, I'm going to start my watch so I know how I'm doing on time. There we go. So it's HPC-centric talk. So HPC is powering amazing breakthroughs for industry. And I want to make a few points. Everything from our nation's defenses, entertaining our families with digital content, designing safer products, predicting the weather, predicting storm paths so that people can take shelter and secure their families. And it goes on and on and on. HPC is an amazing field. And I really don't know the mix of the audience, how many people actually are practitioners in HPC versus how many of you folks are enabling those who are practitioners in HPC. But there's really two things that have made HPC advance over the last decade or so, and it's the computers and the network. But one thing I like to say internally, and this sometimes gets me in a little bit of trouble at Intel, I say hardware made it possible, software made it happen. And it's really true. And I think this community, Open Fabrics, more than anything, made it happen over the last decade. It's been amazing what Open Fabrics has done for HPC, what it's done for cluster computing. You guys should all be very proud of yourselves. And I'm very proud of the part that I've played in helping make this happen with Open Fabrics. So if you just take a look at the numbers, the picture on the left is a tad out of date, but it's a chart I pulled from the Open Fabrics website, tracking the penetration of Open Fabrics in top 500 as a count of machines over the last decade, roughly. And as was mentioned, Open Fabrics was formed in 2004, and in those days, actually in 2003, there were no systems on the top 500 list with InfiniBand. I think we got the first MPI implementation over InfiniBand in late 2002. We actually demonstrated it with two commercial applications, LS Dyna and Fluent, at the Intel Developer Forum on Intel InfiniBand hardware. Do you remember that? Very, very early on, it was a nice collaboration we did with NCSA, and I believe that was the first ever MPI on InfiniBand. And that was an exciting day because the InfiniBand folks had never heard of HPC, and the HPC people had never heard of InfiniBand, and we got the two together. But very quickly, we planted the seed. We got a toehold in the top 500. But it wasn't until Open Fabrics came along and dealt with the fragmented software ecosystem that was out there, as Paul said, that allowed us to have a single focal point. It allowed multiple MPI implementations to target a single set of APIs. It allowed a group to focus on implementing and advancing those APIs. And once that happened, this took off in a way that was amazing. And HPC became the primary consumer of InfiniBand. Okay? And if you look on the right, this is a picture I took from the top500.org website. Orange is Ethernet, and Ethernet has always been a large share, or rising as clusters gained presence in the top 500 and in HPC. And then it started declining again. But the amazing thing is InfiniBand has had steady growth. Sitting on top of that curve, it's a little difficult to see. InfiniBand continues to grow and grow and grow. And at last count, Open Fabrics software is driving 42% of the machines in the top 500. Quite an impressive accomplishment to go from 0 to 42% of the top machines in the world in just a decade, or less than a decade in this case. So very impressive. So Open Fabrics has a rich history. It started with a small group of people trying to figure out how to deal with the fragmentation of the InfiniBand software that was really, it was staring us in the face, and it was threatening to kill InfiniBand. The people in the room who formed OpenIB, which became Open Fabrics, really were genuinely scared that InfiniBand was a great technology and it was not going to survive if we did not address this. So OpenIB was formed. And very quickly, as you look over the years, very quickly we got into Linux, at least a little bit of software into Linux. But year after year, Open Fabrics expanded its scope, or OpenIB expanded its scope, first by becoming Open Fabrics and embracing RDMA Ethernet and iWarp, over time embracing Rocky, and then moving from just a tree of software to an actual distribution to make it more consumable, more accessible, more standard. And with every generation, the user base and the usage of not just Open Fabrics, but of the technologies that enabled InfiniBand and iWarp grew. That's been a very impressive path. And RDMA is the common thread that got us there. But like Paul, I want to talk about whether or not RDMA is really what's fundamental, or is it something else? I think RDMA and InfiniBand and other related fabrics showed the world, and in particular showed the Linux community, that there was value in something beyond traditional fabrics. I'm not sure who made the comment in the last session, but they pointed out that the developers of the traditional networking software stack initially were not open to the idea of a different network stack. They said, why? And I think with InfiniBand and the other fabrics enabled by Open Fabrics, we showed why. We showed the values. We showed what a fast fabric was. RDMA happened to be the vehicle, but it's what those fabrics could do that was valuable, not the specifics of those verbs. And with that, we moved the Linux community to a place where they understood the distinct value of fast fabrics, and they accepted that there needed to be an infrastructure in Linux to host those and advance those and enable those fast fabrics. So again, I want to raise the question, is it really about RDMA? And Paul used the term verbs to mean RDMA, and I'm going to stay away from the word verbs, because verb to me simply is, I'm going to take its English semantic meaning, which is I'm going to tell something what to do. RDMA is one thing I can tell a fabric to do. What are the other things we could tell a fabric to do that would be valuable to us? It's possible to expand our thinking and our notion of verbs to include things beyond RDMA. I want to talk a little bit about what's valuable, where the value is, and what's valuable beyond RDMA that we should be considering as a community. So what makes a fast fabric? I found this nice picture on someone's blog called zcopy.wordpress.com. Little page-and-a-half tutorial on RDMA. And it's probably the cleanest, simplest picture I've seen that gets across the point that an application sits on top of an OS and a NIC. It's got a memory buffer, and it wants to send some data to another application's memory buffer. And while the data obviously has to travel down through the fabric, the arrow connects the buffer directly to the NIC. The application's talking to the NIC. It's not talking through the OS, it's talking around the OS to the NIC. But from the point of view of the application, the data transfer is happening directly between the two buffers. That's exactly what distinguishes fast fabrics from traditional fabrics. You're not asking the OS to do something for you. You ask OS up front to give you permission to do something for yourself. Okay? So what are some of the other characteristics of fast fabric? Well, high bandwidth. There's no point in being efficient if you're slower than the standard things. Low latency. The direct application messaging with kernel bypass, as we discussed. There's also this notion of protection, and that's to ask the OS. And I want to come back to that. With the right mechanisms in place, you ask the OS for permission to do something you normally wouldn't be able to do, which is talk to hardware, and be able to ask the hardware to do things for you. And Open Fabrics has established a framework that allows the OS to trust applications to interact with hardware directly. That's incredibly powerful. And it has nothing to do with RDMA. It has to do with the framework and the protection and the direct access. And again, RDMA is an example of something that we can do. It's one capability of some fast fabrics. There are other fast fabrics that provide these capabilities and don't even implement RDMA, right? And they've been some of them have been quite useful in fields like HPC. I also think it's really important to have a data movement engine. Sometimes data movement engines are implemented with CPUs. Sometimes they're implemented with dedicated hardware. But it's incredibly important to have something that as a programmer, you say, move this data, and you know something's going to move the data for you. And there was a reference to the Intel Xeon Phi. I don't know who made that comment earlier. It was Christoph. In fact, when time came to abstract the PCI network that connects an Intel processor with a card with a coprocessor, we decided to actually do that with, or that card has a data movement engine on it, and we decided to expose that up through a DMA, then RDMA, and ultimately an Open Fabrics interface. And Bob Woodruff, who's here, is actually going to talk a little bit about how that works, both for InfiniBand and inside the box. So it's a very good concept to do this and to exploit a data movement engine. Okay. So now I want to talk a bit about what is it like for an MPI developer on RDMA. And you've probably seen in past conferences whole talks on this. Paul rattled off a quick list, and I'm going to do this in 2 slides. It's very high level. What MPI wants to do is it wants to be able to say MPI send on one side and MPI receive on the other side. It wants to be able to provide a communication context. It wants to be able to tag a message so that it matches a tag on the other side. And it wants to be able to match data types. So there's a certain amount of context that's wrapped around the payload, and it wants to match those. RDMA has the capability to say that this is a message. I want to move from here to here, but it's a raw buffer. What it lacks is that context, the tag, the data type, the communications context that's so inherent to MPI. So MPI wants to do what's on the left. What MPI does is on the right. It first of all says, okay, for small messages, I'm going to have to do something special to get low latency. For large messages, I'm going to have to do something special to exploit the high bandwidth, low overhead that a fast fabric can provide. So a typical implementation is what's known as eager protocol, and I think many people in the room, I don't know if everybody knows this, so I'll just spend a minute on it, where you set up some pre-registered tiny buffers, they're shared, and then you work your way around with a circular queue, plopping in the information, which is the envelope that describes all that matching data, the tags, and you push that across the network directly. On the receive side, you examine the queue, and you remove the messages. So you always get an extra copy. InfiniBand networks and related networks let you do 0 copy, but we give up the 0 copy in order to get low latency so that we can send a message in one shot. When I've got a large message, I do basically the same approach, but there I send the message, I send just the envelope that describes the data. I don't actually send the data. And then when I have a match, I go do an RDMA read and I pull the payload across. That works quite well, and we've had a ton of success with MPI on RDMA. I don't think anyone would claim that InfiniBand and Open Fabrics has not been successful in HPC. Just look at what I showed you before. It's been incredibly successful. But there are software overheads that are associated with those operations, and those are growing as a fraction of the achievable performance, or of the latency, and thus limiting the achievable performance of this approach. And as we as a community look forward to exascale, we have to start thinking about that and say, when are those limitations going to become critical? When are those overheads going to be really painful? Okay. So I just scratched the surface. And some of these, I didn't see Paul's slides in advance, so I apologize for repetition. But what about unexpected message handling? I want to start sending a message, and I don't know if the receive is there on the other side. Do I always have to check? Could I opportunistically send the message, and then if I found out this receive is not ready, pause it? If you look at things like what Miracom did with MX, Miracom's not part of the Open Fabrics community, but if you look at their MX protocol, there's some very interesting ideas in there about how you can start sending a message, and if the receiver's ready, keep sending it. If the receiver's not ready, put hold on it and get the rest of the message later. Those are the kind of concepts that are very friendly to MPI and don't exist in RDMA today. Tag matching, I mentioned. Paul talked a lot about connection management, the complexity and scalability. And I think Sean Hefty is actually going to give a whole talk about scalable subnet administration. I don't know if he's going to get into scalable connection management or not. There's the growing issues of the memory footprint associated with all these buffers that I was showing you to map MPI onto RDMA. So the message here, and it goes on and on, collectives, non-contiguous messages, the unnecessary complexity of having two different protocols, rendezvous and eager, and now having to put a knob in to try and experiment as a user. Where's the right cutoff? What's the right algorithm? I'm sure Susan would tell you that at her site that folks are always playing with the knobs and would rather just know that MPI runs well in this fabric and not have to explore such a large space. And MPI-3 enlarges the space, and PGAS is coming, as Paul said. So reaching exascale is going to require breakthroughs in performance, and it's going to require breakthroughs in energy. We haven't really talked about energy here, and both of those are going to be challenges for RDMA, in my opinion. So let me just give you an example. Exascale means exaflops, 10 to the 18th flops. So if you do the math and you say, well, what kind of power would it take to get us there with the natural evolution of today's technology? It's somewhere north of 100 megawatts, which I think is north of one modern or two slightly aged nuclear power plants to power your machine room, dedicated. And I don't think anyone thinks that's feasible. I don't know, Matt, if they're going to let you build a nuclear power plant to power your machine room? No. So that's a real challenge. Various consumers around the world I think the birds are coming to carry me away.
Should I answer?
Yeah, answer. Let's see who it is.
It's a beach here.
Okay. All right. Bill, hand me that. I'm going to silence it for you. I can do that. Yeah, I know how to do it. This is a Galaxy 3. Good phone. Mute. There we go. All set. Oh, you want me to throw it?
Yeah.
I would not throw a Galaxy 2, otherwise it'll look, or 3, it'll look like mine with cracks in it. I tried it. So continuing in the math, 100 megawatts. I think the exascale stakeholders, the community of exascale stakeholders worldwide have agreed that if we could achieve an exaflop in 20 megawatts, that would be appealing. Does that sound like the right number? It's a real tough challenge. A lot of folks are looking at how we get there. Intel spent a lot of time breaking down the power budget and saying if we had to go from the 100 megawatts, which is how we could build that system with the natural evolution of today's technology, and instead squeeze it to 20 megawatts, everybody's going to be taking a haircut on power. The fabric ends up needing to go from a number that's something like 100 picojoules per flop. So if you want to move data, per flop of machine capacity, you need 100 picojoules of energy allocated to the NIC. That's where we get today. That's already extremely difficult. We've got to improve that 10x, more like 12x. We're thinking the budget for the NIC, or for the fabric, is going to be about 8 picojoules for every flop of machine capability. That is a tiny, tiny power budget. And as it turns out, every time you do a memory copy, every time you do an extra software operation, every time you do an extra round trip on the network to implement a more complex protocol, like Rendezvous, you can very quickly see that you're sending yourself off by factors of 2, 3, and 4. We don't believe that the inefficiencies that exist in implementing MPI over RDMA are going to allow us to get there. And that's why this is becoming critical. So I just want to point out that there's an inherent semantic mismatch between the most common user of fast fabrics and the most common fast fabrics in the world. And that's something that will get addressed. And the question I want to ask this audience is that going to get addressed with Open Fabrics leadership and within Open Fabrics, or is it going to be addressed separately? Because as Paul said, if you don't keep swimming, you die. So what if? What if we had application-centric APIs? And what if software actually led rather than lagging hardware? Open Fabrics has focused on what the standards bodies are putting out and created APIs to access them. It's been incredibly valuable. But what if Open Fabrics actually took the first step and said, the application developers, the upper level protocol developers are telling us they want this. We're going to implement those APIs. Now, hardware companies, I have to silence someone else's phone. Hardware companies might come along and say, hey, how can I build a piece of hardware that plugs into Open Fabrics instead of the other way around? And that would be very powerful because Open Fabrics would actually create a focal point for the industry. It would establish the capabilities that are known to be valued. It It would create a clear target for the hardware vendors. It would create convergence in hardware, as opposed to having hardware and then working for convergence in software, which is where we've been today. So what if open fabrics led the way? Would hardware follow? I can't answer that. But I think there's a chance, and I think it's worth thinking about. Okay? So let's dig in a little bit more of what if open fabrics led. And I think open fabrics is a leadership group, there's no question. But we haven't led the hardware. We've only led the software. What if we led the hardware? And I'm a software guy. I work at Intel, but I'm a software guy. So let's look at the facts. Open Fabrics today is the framework for fast fabrics in Linux. We talked about that before. Linux was not friendly to fast fabrics a decade ago. It's Open Fabrics and the efforts of the people in this room that changed that. That's an incredible position, an incredible accomplishment, and one we don't want to squander. I just want to focus on the fact that it's the framework that's valuable. Okay? It's not just RDMA, it's everything that wraps around it, the protection mechanisms, the discovery mechanisms, the access mechanisms, the trust that we've built with the Linux community to allow us to put something in that OS and give direct access to hardware from application space, something that doesn't exist hardly anywhere else in Linux. Open Fabrics in our software stack is the focal point, not just for the consumers, but also the producers. I've seen companies who build non-InfiniBand, non-native RDMA fabrics come along and say, how can I create an Open Fabrics compatibility layer to get access to that software? I told you the example of Intel Xeon Phi. We actually chose to expose our PCI bus and our DMA engine as an Open Fabrics provider. Why? Because it lets us tap into all the software that's out there. It's very powerful to be the focal point. Open Fabrics has established that position. Let's not squander it. We know that Open Fabrics was dealing with, as a group of people, was dealing with a fragmented and fractured software space back in 2003. And we actually overcame that. But I think the demands on fabrics that are coming from Exascale, coming from Hadoop, coming from financial services needs, coming from the oil and gas community that doesn't quite like MPI the way it is, and so on, coming from parallel file systems, distributed databases, is going to create pressure on this community and lead to software fragmentation again. And again, the question is, can Open Fabrics create an infrastructure that's friendly to those, invites them, and makes them part of the community? Or is it going to say, we do RDMA, and that's going to happen elsewhere? So I think we could see fracturing and fragmentation of the ecosystem again. Open Fabrics has done it once. Maybe we can prevent it happening a second time. I'm a big believer in software first. Software is really hard unless we hire smart software developers, but it's really easy to play around and experiment in software and build a library and hand it to your MPI group, hand it to your Hadoop team, and so on, and say, how does this work for you? And you'll get feedback. It doesn't matter how much design you do in a back room and standards group or wherever trying to create the right APIs. When you hand it to someone and say, please use this, that's when you find out what you got wrong and what could be better, what could be simpler. So software first will actually allow us to get things right. If we get things right, then when hardware comes along to plug in those interfaces, everything's going to be pretty stable. We're not going to have to be working around bugs or issues after the fact. When software interfaces exist and they're consumed, they become a really appealing target for hardware companies. Thus, extant software can lead hardware. And standards, as Paul said, rather than sitting in rooms and trying to figure out what's important and what's next, if Open Fabrics establishes interfaces and says, we need this, and here are the consumers, that's a very strong and powerful pull on standards bodies and will focus their work. The last thing is, you don't want to stifle innovation. And the higher level interface that you provide that's standard, the more flexibility you give to hardware companies to implement things. All their cleverness can plug in, and you're not exposed to the complexity. So think about that. If we provide higher level APIs, we actually may accelerate innovation rather than stall it. Okay, so can Open Fabrics get us there? Here's a really simple software stack from the Open Fabrics site. I think it looks familiar to most of you. But I think if you stare at the thing, you'll notice two things. One is, at the bottom is RDMA hardware. In the middle is all kinds of kernel services designed to control access to and manage the fabric. And then there's a bunch of services in the middle that have figured out how to implement themselves on RDMA, block storage, TCP/IP, and so on. Some of them are very natural, some are kind of unnatural. And then across the top, you have all these different things that are accessing the fabric as well. MPI and distributed computing is, I'd say, chief among them. And I showed you some of the challenges. But there's a ton that's in Open Fabrics today that has nothing to do with RDMA. It has to do with access, control, again, the trust with the community. So my belief is that Open Fabrics actually has the foundation here to take RDMA as the first example of something great we've done with Fast Fabrics and Linux, and now start lining up additional capabilities alongside it. And if we like the word verbs, let's use the word verbs to talk about access to and control of those new capabilities beyond RDMA, and including RDMA. It's not going away. If we don't like the word verbs, we think it's too tied to RDMA, then let's come up with a new word. But the point is, it's time to start stacking up some capabilities alongside RDMA so that Open Fabrics remains the focal point of Fast Fabrics in Linux and the industry. So beyond, the plausibility that the stack as it exists today has the main things we need. Certainly it'll need changes, and it's going to require a lot of hard work from people in this group. But I think there's also a lot of prior work we can go look at outside of Open Fabrics. I mentioned MX from Miracom. There's MXM that Mellanox is doing, PSM that came out of QLogic, now sits with Intel. Oh, that's supposed to say TMI, not TSM, but I think I just invented something new. TMI, the tag matching interface that Intel put out as a way for fabrics other than RDMA to plug in efficiently to MPI. There's portals, which we'll hear more about today. There's a lot of good work out there, but there's a lot of them. How do we come together and figure out what are the basic building blocks of communication that are going to be valuable across a wide range of areas? We also have prior work that shows that you can actually do these things alongside RDMA. Almost 10 years ago, we created an extension framework for DAPL, which is an RDMA interface that's cross-OS and precedes Open Fabrics, and showed that you can do things like discover capabilities beyond RDMA, like the ability to do collectives and actually use those inside the software and have it coexist. So I think this is very plausible. I think whatever we need to do, though, we need to understand that if you establish the software APIs first and you're drawing the hardware along, you've got to be able to discover what the capabilities are of the fabric and allow the software to react to what's, make it visible what's in hardware, what's being done in software, what's fast, what's slow, so that software can make smart choices, but over time it can evolve. So suppose a fabric has a capability of avoiding memory registration, it'll do it for you. Software discovers that. It says, oh, you don't do memory registration? Okay, I'll register my memory before I do it. Later, it's harmless if you do the memory registration, but ultimately you can detect that and you can turn it off in the software. So the software and the hardware start to become things that can evolve forward in time. Discoverability and long-lived interfaces are critical to making that happen. So where should we start? MPI is obvious. It's the biggest user of InfiniBand today, in my opinion. The MPI 3 standard just came out. It gives us an opportunity to take a fresh look at what's going to be valuable next to this community. PGAS languages and PGAS libraries and PGAS concepts. I don't want to focus on UPC and Core Fortran necessarily, or GasNet. I want to focus on the concepts that exist in the global address space. They're increasing in value. And how can we enable them and make it very natural versus perhaps unnatural? Parallel file systems, block storage, can take really great use of RDMA today, but some of the file access is moving to block-based interfaces. Very, very different. And maybe RDMA is not quite right for them. And then I think you'll see representatives in the room. We have Oracle here, and we have folks from the financial services community. They have needs that are different from MPI. How do we service their needs? So what are some of these common building blocks that are distinct from RDMA that we could define and enable a whole class of software to run more efficiently on Fast Fabrics? So to wrap up, I think we should get started. I'm a big believer in software leading hardware. I don't think that we're necessarily going to get exactly what we want if we wait for standards bodies to figure it out. Let's say what we want and show them the way. Let's build on Open Fabric's established industry position not lose it. Embrace the software, start developing these APIs, and iterate. Let's build some software implementations of the hardware we want and see where it goes. So let's keep Open Fabrics the home for fast fabrics. Thank you.
Thank you very much, Bill. Questions? We've got 5 minutes before we get a cup of coffee. Some questions? Okay, so I'm going to do what I used to do many years ago when we were getting going. There's been a call here from both Paul and from Bill for Open Fabrics to start to look at things that we haven't really looked at before, and to start to work on improving the software to achieve some of these things, and also a very interesting call to start get ourselves into a position where people who are building hardware want to build to what our software does. So 2 or 3 years ago at this point, I would call for volunteers to form a working group within the Alliance to work on these things and move forward on the directions that we've discussed in these workshops. So I'm going to do that again. Right? Let's see if we can't get a working group of us, amongst us, working on a regular basis together, obviously on a volunteer basis, to move ahead on some of the things that Paul and Bill have been talking about. Right? So you know who our leaders are, right? Contact them and talk to them. In the old days, I used to call for hands for a volunteer to lead it, but maybe we've gone beyond that. Have we, Jim, or not? I mean, it'd be great if somebody said they'd like to lead that. We need a leader of the working groups, right? Over coffee, perhaps we might talk about that. We might have somebody step forward to say, okay, I'm going to lead this. I really need this for my organization. I'm going to lead this. Okay, let's get some coffee in. Thank you very much, Bill.
Thanks.